The speed of light is the fastest thing in the universe, the ultimate limit that shapes our perception of time and space. It travels at an incredible 299,792,000 kilometers per second through the vacuum of space. This cosmic speed limit has fascinated scientists and dreamers alike for over a century. But what if that boundary could be crossed? What if aliens, somewhere in the distant cosmos, figured out how to break the speed of light barrier? Imagine civilizations millions of years ahead of us, with technology so advanced that they have discovered ways to bend the very fabric of space and time. Perhaps they have unlocked secrets that allow them to journey between stars in the blink of an eye, while we are still bound by the laws of physics as we know them today. These alien travelers might be crossing vast distances in moments that would take us thousands of years to cover, even at our fastest speeds. The question that haunts us is simple yet profound. Would we ever notice if such beings existed? Would we be able to detect their faster-than-light journeys across the galaxy? Or would they remain invisible to us, moving through space in ways that our current understanding of the universe cannot even comprehend? Tonight, we explore this fascinating possibility, diving deep into the mysteries of light speed travel and the potential signs we might look for in our search for extraterrestrial life. We will contemplate the implications of faster-than-light travel and whether it would change our universe in ways we cannot yet imagine. As we gaze up at the stars, we wonder about the countless civilizations that might exist beyond our world and whether some of them have already discovered the key to transcending the ultimate speed limit. The cosmos holds infinite secrets, and perhaps the greatest secret of all is whether the speed of light truly represents an unbreakable barrier or simply a challenge waiting to be overcome by minds far more advanced than our own. Join us as we journey through the possibilities, exploring what it would mean for humanity if aliens have indeed broken the speed of light, and how we might one day detect their presence among the stars. From our tiny blue planet, we look out into the vastness of space, knowing that somewhere in that infinite expanse, there may be beings who have already solved the greatest puzzle of physics. The story of our universe is far from finished, and tonight, we begin to explore one of its most intriguing chapters. To understand whether aliens could break the speed of light, we must first grasp what makes this cosmic speed limit so special. Light travels at exactly 299,792,458 meters per second in a vacuum. This number is not just fast, it is the fastest speed at which any information or energy can travel through space. When we look up at the night sky, we are literally looking back in time. The light from the nearest star beyond our sun, Proxima Centauri, takes over 4 years to reach Earth. This means we see it as it was 4 years ago, not as it is right now. The light from distant galaxies has been traveling for billions of years before reaching our telescopes, showing us the universe as it existed in the ancient past. This speed limit shapes everything we know about the cosmos. It determines how quickly information can travel from one place to another, how we communicate across vast distances, and even how we understand the flow of time itself. The speed of light is woven into the very fabric of space and time, creating what scientists call space-time. Light behaves in remarkable ways that still puzzle scientists today. Sometimes it acts like a wave, spreading out and interfering with itself. Other times it behaves like tiny particles called photons, carrying packets of energy across the universe. These photons have no mass, which is precisely why they can travel at the ultimate speed limit. Anything with mass would require infinite energy to reach light speed, making it impossible under our current understanding of physics. The significance of light speed goes far beyond just being fast. It represents a fundamental property of our universe, a constant that never changes, regardless of who is measuring it or how they are moving. Whether you are standing still on Earth or traveling in a spacecraft at tremendous speeds, you will always measure light moving at the same speed relative to you. This strange fact was one of the key insights that led Albert Einstein to develop his theory of relativity. Throughout human history, we have gradually discovered that light speed is not infinite. Early scientists thought light traveled instantaneously, but careful experiments in the 1600s and 1700s revealed that light takes time to travel from place to place. The Danish astronomer Ole Romer first measured the speed of light in 1676 by observing the moons of Jupiter and noticing tiny delays in their eclipses as Earth moved closer to and farther from the giant planet. As our understanding of light improved, so did our measurements of its speed. Scientists used increasingly sophisticated methods, from rotating mirrors to laser interferometry, to pin down this crucial number with incredible precision. Today, we know the speed of light so accurately that we use it to define the meter itself, making it one of the most precisely known constants in all of physics. The French physicist Hippolyte Fizeau conducted one of the first terrestrial measurements of light speed in 1849. He used a spinning gear wheel with gaps between the teeth, shining light through the gaps toward a distant mirror. By carefully adjusting the speed of the wheel, he could measure how long it took light to make the round trip. His result was remarkably close to the true value, proving that light indeed had a finite speed, even over relatively short distances on Earth. Later, Albert Michelson refined these techniques using rotating mirrors and incredibly precise timing mechanisms. His measurements in the late 1800s were so accurate that they remained the standard for decades. Michelson's work not only gave us a better understanding of light speed, but also led to the famous Michelson-Morley experiment, which helped pave the way for Einstein's revolutionary theories about space and time. The story of measuring light speed reveals something profound about the nature of scientific discovery. Each generation of scientists built upon the work of those who came before, using better tools and more sophisticated methods to probe deeper into the mysteries of the universe. What started as a simple question about whether light travels instantly became a journey that transformed our understanding of reality itself. Light also carries with it the story of the universe itself. Every photon that reaches our eyes or our instruments has traveled unimaginable distances, carrying information about stars being born, planets forming, and galaxies colliding. When we capture light from the most distant objects in the universe, we are literally seeing the cosmos as it was over 13 billion years ago, shortly after the Big Bang itself. This connection between light and time creates one of the most beautiful aspects of astronomy. We are time travelers every time we look up at the night sky. The moon we see is 1.5 seconds in the past. The sun appears as it was 8 minutes ago. The constellation Orion shows us stars as they were hundreds of years ago. And the farthest galaxies reveal themselves as they existed when the universe was young and very different from today. Consider the implications of this cosmic time delay. If a massive star in the Andromeda galaxy exploded today, we would not see that explosion for over 2 million years. By the time its light reaches us, entire civilizations might have risen and fallen on Earth. This means that our view of the universe is always outdated, always showing us the past rather than the present. We live in a universe where the present moment exists only locally, and everything distant is a memory preserved in light. The speed of light also determines how life itself might spread across the galaxy. If civilizations exist on distant worlds, any signals they send to us must obey this cosmic speed limit. A radio message from a planet orbiting the nearest star would take over 4 years to reach us, and our reply would take another 4 years to get back to them. This creates a fundamental challenge for interstellar communication, turning any conversation into a decades-long exchange. Imagine trying to have a simple conversation with beings living around Alpha Centauri, our nearest stellar neighbor. You ask them about their weather, and nearly 9 years later, you finally receive their response. By then, you might have forgotten what you asked, and their weather would certainly have changed many times over. This time, delay makes real-time communication impossible across interstellar distances, forcing any spacefaring civilization to think in terms of generations rather than moments. Scientists have wondered whether there might be ways around this limitation. Some theoretical physicists have proposed exotic concepts like quantum entanglement, where particles seem to influence each other instantly across vast distances. Others have explored the possibility of using gravitational waves, ripples in space-time itself, as a faster means of communication. But so far, all of these ideas still respect the speed of light as the ultimate barrier for transmitting information. The phenomenon of quantum entanglement has captured the imagination of scientists and science fiction writers alike. When two particles become entangled, measuring one instantly affects the other, regardless of the distance between them. This seems to violate the speed of light limit, but physicists have shown that no actual information travels faster than light in this process. The entangled particles share a mysterious connection, but that connection cannot be used to send messages or signals. The measurement of light speed has become one of the most precise achievements in all of science. Using atomic clocks and laser technology, we can now measure this speed to within a few parts per billion. This incredible precision allows us to test some of the most fundamental theories in physics and to search for any tiny variations that might hint at new physics beyond our current understanding. Modern experiments use sophisticated laser interferometry to measure light speed with extraordinary accuracy. These experiments can detect changes in distance smaller than 1,000th of the width of a proton, allowing scientists to probe the very foundations of space-time itself. The precision of these measurements is so great that they have been used to detect gravitational waves, tiny ripples in space-time caused by the collision of black holes billions of light years away. What makes light speed even more mysterious is that it appears to be built into the very structure of reality itself. It shows up in equations describing electricity and magnetism, in the mathematics of quantum mechanics, and in the geometry of space-time. It is as if the universe itself has chosen this particular speed as a fundamental organizing principle, weaving it into every aspect of how matter and energy behave. The speed of light appears in Einstein's most famous equation: energy equals mass times the speed of light squared. This simple formula reveals the tremendous amount of energy locked inside even the smallest amount of matter. It explains how stars shine, how nuclear reactions work, and how the universe itself generates the energy that powers galaxies and creates the elements necessary for life. But perhaps most intriguingly, the speed of light may not be the absolute final word on cosmic speed limits. Some theories suggest that in the very early universe, during a period called cosmic inflation, space itself expanded faster than light. This does not violate relativity because space itself was expanding, not matter or energy moving through space. This hints that there might be ways to effectively travel faster than light by manipulating space-time rather than simply moving through it. As we stand on the threshold of deeper space exploration, the speed of light remains our greatest challenge and our most fundamental guide. It defines the boundaries of what seems possible, while simultaneously hinting at the vast mysteries that lie beyond our current understanding. Perhaps somewhere in the cosmos, beings far more advanced than ourselves have found ways to transcend this barrier, opening up possibilities that we can barely begin to imagine. The question of whether aliens could break the speed of light brings us to the edge of known physics and into the realm of speculation and wonder. If such beings exist, they would possess technology so advanced that it might seem like magic to us. They would have unlocked secrets of the universe that we are only beginning to glimpse, and their presence might be detectable in ways we have not yet learned to recognize. As we venture deeper into the mysteries of cosmic speed limits, we encounter one of the most mind-bending aspects of our universe. What actually happens when something approaches the speed of light? The answer reveals why this cosmic barrier seems so impossible to cross, and yet hints at the extraordinary possibilities that might await any civilization clever enough to find a way around it. Albert Einstein's theory of special relativity, published in 1905, fundamentally changed our understanding of space, time, and speed. According to this theory, strange things begin to happen as objects approach light speed. Time itself starts to slow down, mass increases dramatically, and the energy required to go faster grows toward infinity. These effects are not just theoretical curiosities. They are real phenomena that have been measured and confirmed countless times in laboratories around the world. Imagine you are traveling in a spacecraft that can somehow approach the speed of light. As your velocity increases, time aboard your ship would begin to pass more slowly compared to time on Earth. This effect, called time dilation, means that a journey that takes years from your perspective might span decades or even centuries for people back home. The faster you travel, the more pronounced this effect becomes, until at light speed itself, time would essentially stop from the perspective of outside observers. This time dilation effect has been directly observed in particle accelerators, where subatomic particles traveling at nearly light speed live much longer than they should according to their normal lifespans. Muons, which typically decay in microseconds, can persist for much longer when accelerated to high speeds. This is not because the particles themselves change, but because time itself behaves differently at such extreme velocities. The energy required to accelerate any object with mass to light speed presents an even more formidable barrier. As velocity increases, the energy needed to go faster grows exponentially. By the time an object reaches 99% of light speed, it requires enormous amounts of energy to gain even a tiny bit more velocity. To actually reach 100% of light speed would require infinite energy, which is physically impossible. Consider a simple example. A grain of sand accelerated to 99.9% of light speed would carry more kinetic energy than a speeding train. At 99.99% of light speed, that same grain would contain as much energy as a nuclear bomb. This exponential growth in energy requirements creates an insurmountable wall that prevents any material object from reaching light speed through conventional acceleration. The mass of an object also appears to increase as it approaches light speed, though this is actually a consequence of how energy and momentum behave at high velocities. From the perspective of a stationary observer, a fast-moving object becomes more resistant to further acceleration, as if it were getting heavier. This relativistic mass increase adds another layer to the impossibility of reaching light speed through brute force acceleration. These effects combine to create what physicists call the light speed barrier. No matter how powerful your engines, no matter how much energy you have available, you cannot simply accelerate past this cosmic speed limit. The laws of physics themselves conspire to prevent it, making light speed an asymptotic limit that can be approached but never quite reached by anything with mass. Yet the universe seems to taunt us with the existence of massless particles that travel at exactly light speed all the time. Photons, the particles of light itself, zip along at the ultimate speed because they have no mass to hold them back. From a photon's perspective, if it could have one, its journey from a distant star to your eye happens instantaneously. The photon experiences no passage of time during its billion-year voyage across the cosmos. Neutrinos, nearly massless particles produced in nuclear reactions, travel at speeds so close to light speed that the difference is almost impossible to measure. These ghostly particles stream through space and matter alike, barely interacting with anything in their path. Trillions of neutrinos pass through your body every second. most of them created in the nuclear furnace of the Sun 8 minutes ago. The cosmic speed limit also affects information itself. According to relativity, no information can travel faster than light, regardless of how it is encoded or transmitted. This means that the speed of light represents not just a barrier for matter and energy, but for knowledge and communication as well. Any signal, whether it is a radio wave, a laser pulse, or even a gravitational wave, must respect this fundamental limit. This information speed limit has profound implications for how the universe works. It means that events in space cannot influence each other instantaneously. When the Sun suddenly disappeared, we would continue to see its light and feel its gravitational pull for 8 minutes before realizing anything had changed. This delay in the propagation of information helps maintain the logical structure of cause and effect throughout the cosmos. The peculiar nature of time at high speeds leads to fascinating thought experiments. If you could somehow observe someone approaching light speed from the outside, you would see them moving in slow motion, their clocks running slower and slower until they almost stopped. Meanwhile, from their perspective, the rest of the universe would appear to speed up dramatically. Entire civilizations might rise and fall in what seems like moments to the high-speed traveler. This time dilation effect suggests intriguing possibilities for space travel, even without breaking the light speed barrier. A spacecraft traveling at 99.9% of light speed could reach distant stars in what feels like months or years to the crew, while decades or centuries pass on Earth. This is sometimes called the twin paradox, where a space-traveling twin would return to find their Earth-bound sibling much older, or perhaps long dead. But the energy requirements for such journeys remain staggering by current standards. To accelerate even a small spacecraft to these relativistic speeds would require more energy than our entire civilization currently produces. The fuel needed would be so massive that carrying it would make the journey impossible using conventional rockets. This energy barrier represents one of the greatest challenges facing any species hoping to explore the galaxy. Some theoretical physicists have proposed exotic solutions to the energy problem. Antimatter, the mirror image of ordinary matter, releases tremendous energy when it meets its normal matter counterpart. A perfect matter, antimatter engine could, in principle, achieve much higher efficiencies than any chemical or nuclear rocket. However, producing and storing antimatter remains far beyond our current technological capabilities. Fusion ramjets represent another speculative possibility. Such a spacecraft would scoop up hydrogen from the thin gas between stars and use it as fuel for continuous fusion reactions. This could theoretically allow for sustained acceleration over long periods, gradually building up to significant fractions of light speed. However, the technical challenges of such a system are immense, requiring advances in magnetic field technology and fusion physics that may take centuries to achieve. The light speed barrier also creates interesting paradoxes when we consider advanced alien civilizations. If they exist and have been traveling between stars for millions of years, why have we not detected them? One possible answer is that the energy requirements for interstellar travel are so enormous that even highly advanced civilizations rarely attempt it. Perhaps the galaxy is filled with intelligence, but each species remains largely confined to its home star system by the tyranny of the light speed limit. Alternatively, alien civilizations might have discovered ways to work around the speed of light restriction without actually violating it. They could use time dilation to their advantage, sending long-lived robotic probes on journeys that span thousands of years. From the perspective of these probes, traveling at very high relativistic speeds, the journey might seem much shorter due to time compression effects. The speed of light barrier might also explain why we have not been visited by alien tourists or conquerors. The enormous energy costs and time commitments required for interstellar travel make casual visits between star systems impractical, even for civilizations far more advanced than our own. Each journey would represent a massive undertaking, carefully planned and executed over multiple generations. Yet the universe may hold surprises that could change everything we think we know about cosmic speed limits. Quantum mechanics already shows us phenomena that seem to violate common sense, from particles that exist in multiple places simultaneously to connections that span vast distances instantaneously. Perhaps there are aspects of physics that we have not yet discovered, loopholes in the laws of relativity that could allow for faster-than-light travel. The study of cosmic rays, high-energy particles that strike Earth's atmosphere from deep space, has revealed particles with energy so extreme that they challenge our understanding of physics. Some of these particles carry more energy than anything we can produce in our most powerful accelerators. If such energies exist naturally in the universe, perhaps advanced civilizations could harness them for purposes we cannot yet imagine. As we push the boundaries of our understanding, the speed of light remains both a fundamental limit and a tantalizing challenge. It defines the structure of space-time, governs the flow of information throughout the cosmos, and sets the ultimate speed limit for exploration and communication. Yet it also hints at the vast possibilities that might await any civilization clever enough to find ways around this cosmic barrier, opening up realms of possibility that stretch the imagination and challenge our deepest assumptions about the nature of reality itself. While the speed of light appears to be an unbreakable barrier, the human imagination refuses to accept such limitations. Throughout history, scientists and dreamers have searched for loopholes in the laws of physics, ways to circumvent the cosmic speed limit without actually violating the fundamental principles of relativity. These theoretical methods of faster-than-light travel push the boundaries of known physics and hint at possibilities that could revolutionize our understanding of the universe. The key insight that drives most faster-than-light theories is that while nothing can move through space faster than light, space itself might be manipulated in ways that effectively allow faster-than-light travel. This distinction is crucial because Einstein's relativity only prohibits objects from moving through space-time faster than light, but it says nothing about manipulating space-time itself. One of the most famous theoretical approaches is the Alcubierre warp drive, proposed by physicist Miguel Alcubierre in 1994. This concept involves contracting space in front of a spacecraft while expanding space behind it, creating a bubble of curved space-time that carries the ship along faster than light. The spacecraft itself never exceeds light speed relative to the space immediately around it, but the manipulation of space-time allows it to cover vast distances in remarkably short times. Imagine space as a flowing river and your spacecraft as a leaf floating on the surface. Normally, the leaf cannot move faster than the current allows, but if you could somehow speed up the current in your local area, the leaf would be carried along much faster without actually moving quickly relative to the water around it. The Alcubierre drive works on a similar principle, manipulating the flow of space-time itself to achieve effective faster-than-light travel. The energy requirements for an Alcubierre drive are staggering, initially calculated to require more mass energy than exists in the observable universe. However, subsequent refinements of the theory have reduced these requirements significantly. Some proposals suggest that exotic matter with negative energy density could make such drives feasible, though no such matter has ever been observed and its existence remains purely theoretical. Negative energy density is one of the strangest concepts in theoretical physics. Unlike normal matter and energy, which curve space-time in ways that attract other objects, negative energy would create repulsive gravitational effects. This exotic substance could theoretically be used not only for warp drives, but also for creating traversable wormholes and other exotic space-time structures. Wormholes represent another theoretical pathway to faster-than-light travel. These are hypothetical tunnels through space-time that could connect distant regions of the universe, allowing travelers to take shortcuts across vast cosmic distances. Think of the universe as a folded piece of paper. While ants walking on the surface must travel the long way around, a wormhole would be like poking a pencil through the paper, creating a direct connection between distant points. Einstein and Nathan Rosen first described these space-time tunnels in 1935, leading to their technical name of Einstein-Rosen bridges. However, these natural wormholes would be incredibly unstable, collapsing almost instantly unless held open by exotic matter with negative energy density. Even if such wormholes could exist, traversing them might be impossible due to intense gravitational forces and radiation. The concept of traversable wormholes was later developed by physicist Kip Thorne and his colleagues, who showed that with the right kind of exotic matter, it might be possible to create stable wormholes that could be safely traveled. These would require threading the wormhole with matter that has negative energy density, creating a kind of cosmic highway between distant parts of the universe. Quantum mechanics offers its own tantalizing hints about faster-than-light phenomena. Quantum tunneling allows particles to appear on the other side of energy barriers seemingly instantaneously, as if they had traveled faster than light through the barrier. While this effect has been observed in laboratory experiments, it remains unclear whether information actually travels faster than light during tunneling events. Some experiments have suggested that quantum tunneling might allow for faster than light information transfer over very short distances. Particles have been observed tunneling through barriers in times that seem impossibly short, leading to speculation about quantum shortcuts through space-time. However, the interpretation of these results remains highly controversial among physicists. Quantum entanglement presents another puzzle that seems to involve faster-than-light connections. When two particles become entangled, measuring one instantly affects the state of the other, regardless of the distance between them. Einstein famously called this spooky action at a distance and was deeply troubled by its implications for the nature of reality. While quantum entanglement does involve instantaneous correlations across space, physicists have shown that it cannot be used to transmit information faster than light. The correlations exist, but they cannot be controlled in ways that would allow faster than light communication. However, some theorists have speculated about ways to exploit quantum effects for faster than light travel or communication that have not yet been discovered. Extra dimensions beyond the familiar 3 dimensions of space and 1 dimension of time could potentially provide shortcuts for faster than light travel. String theory and other advanced physics theories suggest that our universe might have additional spatial dimensions that are curled up too small for us to perceive directly. If advanced civilizations could access these extra dimensions, they might be able to take shortcuts through higher dimensional space. Think of this like a subway system beneath a city. People walking on the surface must follow the streets and navigate around buildings, but the subway tunnels provide direct routes underground. Similarly, extra dimensions might provide hidden pathways through the universe that allow for much faster travel between distant points in ordinary 3-dimensional space. The mathematics of higher dimensions is incredibly complex, but some calculations suggest that travel through extra dimensions could theoretically allow for effective, faster than light movement. A journey that takes years through normal space might be completed in minutes if travelers could somehow access these hidden dimensions of reality. Tachyons represent another theoretical possibility for faster than light phenomena. These hypothetical particles would always travel faster than light, existing in a realm beyond the normal speed limit of the universe. While tachyons have never been observed, their mathematical properties suggest they would experience time differently than normal matter, possibly even traveling backward in time. If tachyons exist, they could potentially be used for faster than light communication or even time travel. Advanced civilizations might have learned to detect, manipulate, or create tachyonic particles for instantaneous communication across the galaxy. However, tachyons also create logical paradoxes that make many physicists skeptical about their existence. The manipulation of gravity itself offers another potential pathway to faster than light travel. Gravitational fields affect the flow of time and the curvature of space, suggesting that sufficiently advanced technology might be able to create artificial gravitational effects that enable faster than light travel. This could involve creating intense gravitational fields, manipulating gravitomagnetic effects, or exploiting other exotic properties of gravity that we do not yet understand. Frame dragging is a real effect predicted by general relativity, where rotating massive objects drag space-time along with them. Spinning black holes create this effect on a cosmic scale, warping space-time in their vicinity. Some theorists have proposed that artificial frame dragging effects could be used to manipulate space-time in ways that enable faster than light travel. The concept of closed time-like curves, paths through space-time that loop back to their starting point in time, suggests other exotic possibilities. While these would violate causality and create paradoxes, they represent solutions to Einstein's equations under certain extreme conditions. Advanced civilizations might have found ways to exploit such exotic space-time geometries for faster than light travel or communication. Vacuum engineering represents another speculative approach to faster than light travel. Empty space is not truly empty, but filled with quantum fluctuations and virtual particles that constantly appear and disappear. Some theorists have proposed that these quantum properties of the vacuum could be manipulated to create exotic effects, including faster than light travel or communication. The Casimir effect demonstrates that the quantum vacuum has real measurable properties. When two metal plates are placed very close together in a vacuum, quantum fluctuations create a small attractive force between them. This proves that empty space has structure and energy that might potentially be manipulated by sufficiently advanced technology. Some proposals involve using intense electromagnetic fields to modify the properties of the quantum vacuum, potentially creating regions where the effective speed of light is different. While these ideas remain highly speculative, they suggest that even empty space might hold secrets that could enable faster than light phenomena. The search for faster than light travel pushes us to the very edges of known physics and beyond. While none of these theoretical approaches have been proven possible, they represent humanity's refusal to accept limitations and our endless drive to explore the cosmos. If alien civilizations exist and have had millions of years to develop their technology, they might have discovered principles of physics that remain hidden from us. Perhaps these advanced beings have learned to manipulate space-time itself, threading wormholes across the galaxy or surfing waves in the fabric of reality. They might harness exotic forms of matter and energy that we have never imagined, opening doorways to faster than light travel that seem like magic to our current understanding. The theoretical foundations for faster than light travel continue to evolve as our understanding of physics deepens. Each new discovery in quantum mechanics, relativity, and cosmology offers fresh possibilities and new ways to think about the fundamental nature of space, time, and motion. While the light-speed barrier remains formidable, the universe may yet hold surprises that could transform our understanding of what is possible and open pathways to the stars that we have not yet learned to see. The question of whether we could detect faster than light travel by alien civilizations strikes at the heart of one of the greatest challenges in astronomy. Our entire understanding of the universe is built upon observations of light and other electromagnetic radiation that obey the cosmic speed limit. If beings somewhere in the galaxy have transcended this barrier, would their activities leave any traces that our instruments could detect, or would they remain forever invisible to our light-based methods of observation? The fundamental problem lies in the very nature of how we observe the universe. Every telescope, radio dish, and detector we have built is designed to capture electromagnetic radiation, traveling at light speed. When we look out into space, we are essentially waiting for photons that began their journey years, centuries, or millennia ago to finally reach our instruments. This creates a cosmic time delay that shapes everything we know about distant objects. Consider what happens when we observe a distant star. The light we see left that star years ago, carrying information about its brightness, color, and motion at that time. If aliens were using faster-than-light travel near that star today, we would not see any evidence of their activities until light from those events finally reaches us years from now. This creates a fundamental blind spot in our observations, a gap between what is happening now and what we can actually detect. This temporal blindness becomes even more problematic when we consider that faster-than-light phenomena might not produce light at all. If alien spacecraft are manipulating space-time itself to achieve their incredible speeds, they might be operating in ways that are completely invisible to electromagnetic radiation. They could be warping space, threading through wormholes, or exploiting exotic physics that leaves no optical signature whatsoever. However, the absence of light does not necessarily mean the absence of all detectable effects. Faster-than-light travel would likely involve enormous energies and exotic matter that could create gravitational disturbances, unusual particle emissions, or other phenomena that might be observable with the right instruments. The challenge lies in knowing what to look for and having sensitive enough equipment to detect such subtle effects. One promising avenue for detection involves gravitational waves, ripples in space-time itself that travel at light speed, but carry information about massive accelerating objects. When black holes collide or neutron stars merge, they create gravitational waves that can be detected by incredibly sensitive instruments like LIGO and Virgo. If alien spacecraft were manipulating space-time for faster-than-light travel, they might create similar disturbances that could be detected across interstellar distances. The creation of an Alcubierre warp bubble, for instance, would involve contracting space in front of a spacecraft and expanding it behind. This manipulation of space-time geometry would likely produce gravitational waves as the bubble forms, moves, and dissolves. These waves would carry a distinctive signature that might be recognizable as artificial rather than natural, potentially alerting us to the presence of advanced technology. Similarly, the opening and closing of traversable wormholes would create massive gravitational disturbances. The exotic matter required to keep such wormholes stable would have unusual gravitational properties that might be detectable from great distances. Even if we could not see the wormhole itself, we might be able to observe its gravitational effects on nearby matter and energy. The energy requirements for faster-than-light travel are so enormous that they might create detectable side effects even if the travel mechanism itself remains invisible. Any civilization capable of generating the exotic matter and energy fields needed for warp drives or wormholes would likely be manipulating forces on scales that dwarf anything in our current technology. Such activities might produce characteristic energy signatures, particle emissions, or electromagnetic disturbances that could be detected by our instruments. Neutrino astronomy offers another potential window into faster-than-light phenomena. Neutrinos are nearly massless particles that interact very weakly with matter, allowing them to travel vast distances through space without being absorbed or deflected. If faster-than-light travel involves high-energy processes, it might produce distinctive neutrino signatures that could be detected by underground neutrino observatories around the world. The manipulation of exotic matter with negative energy density required for many faster-than-light theories would likely produce unusual neutrino emissions. These particles would carry information about the extreme physics involved in creating and maintaining faster-than-light travel systems. While neutrinos are notoriously difficult to detect, their ability to travel through matter means they could provide direct evidence of activities that remain invisible to light-based observations. Cosmic ray astronomy might also reveal evidence of faster-than-light technology. Ultra-high energy cosmic rays, particles with energies far beyond anything we can produce in our accelerators, regularly strike Earth's atmosphere from unknown sources in deep space. Some of these particles carry so much energy that their origins remain mysterious. If advanced civilizations are manipulating matter and energy on cosmic scales for faster-than-light travel, They might be responsible for some of these extreme energy cosmic ray events. The search for artificial gravitational lensing effects could provide another detection method. Massive objects bend light around them, creating gravitational lenses that magnify and distort the images of more distant objects. If alien civilizations were using massive artificial structures or exotic matter configurations for faster than light travel, they might create unusual lensing effects that could be spotted by careful analysis of astronomical observations. Temporal anomalies represent one of the most intriguing possibilities for detecting faster-than-light phenomena. Many theories of faster-than-light travel involve manipulations of time as well as space, potentially creating regions where time flows differently than normal. While these effects would be incredibly subtle, they might be detectable through precise timing measurements of pulsars, atomic clocks, or other highly regular astronomical phenomena. The concept of faster-than-light communication raises additional detection possibilities. If aliens are using tachyons, quantum entanglement, or other exotic methods to communicate instantaneously across interstellar distances, their signals might create detectable disturbances in the quantum vacuum or other subtle effects that our instruments could potentially observe. One of the most challenging aspects of detecting faster-than-light phenomena is that we might not recognize the signatures even if we observe them. Our current understanding of physics is built upon the assumption that nothing travels faster than light. So any faster-than-light effects might appear as anomalies, glitches, or unexplained observations that we dismiss as instrumental errors or natural phenomena we do not yet understand. The history of astronomy is filled with discoveries that initially appeared as mysterious anomalies before being recognized as new phenomena. Pulsars were first detected as mysterious radio signals, so regular they were briefly considered possible alien beacons. Gamma ray bursts appeared as unexplained flashes of energy before being understood as the most powerful explosions in the universe. Perhaps some of the unexplained observations in our astronomical data already contain evidence of faster-than-light technology that we have not yet learned to interpret. The development of increasingly sensitive instruments continues to expand our ability to detect subtle phenomena that were previously invisible. Gravitational wave detectors have opened an entirely new window on the universe, revealing black hole mergers and neutron star collisions that were completely undetectable just a few decades ago. Similarly, advances in neutrino detection, cosmic ray astronomy, and high-precision timing measurements might soon make it possible to observe effects that are currently beyond our reach. Machine learning and artificial intelligence are also revolutionizing our ability to find patterns in astronomical data. These systems can analyze vast data sets, looking for subtle correlations and anomalies that human researchers might miss. If faster-than-light phenomena produce characteristic signatures hidden in the noise of our observations, AI systems might be the key to recognizing these patterns and alerting us to the presence of advanced alien technology. The search for techno-signatures, artificial signals that indicate the presence of advanced civilizations, is expanding beyond traditional radio astronomy to include many of these exotic detection methods. Researchers are developing new strategies for recognizing artificial gravitational wave signals, unusual neutrino emissions, and other potential indicators of faster-than-light technology. While these searches are still in their early stages, they represent our best hope for detecting civilizations that have transcended the light-speed barrier. One of the most profound challenges in detecting faster-than-light travel is the possibility that it operates on entirely different principles than anything in our current understanding of physics. If aliens have discovered new laws of nature or exotic physics that we have not yet imagined, their faster-than-light activities might be fundamentally undetectable by any instruments based on our current knowledge. This raises the unsettling possibility that the galaxy might be filled with faster-than-light traffic that we cannot even begin to perceive. Advanced civilizations might be conducting regular commerce, communication, and exploration using methods so far beyond our understanding that we remain completely unaware of their activities. We might be like primitive people trying to detect aircraft using only their sense of hearing, missing most of the activity happening in the skies above. However, the laws of physics seem to be universal, and any faster than light technology must still operate within some version of these fundamental principles. Even if aliens have discovered exotic loopholes in relativity or quantum mechanics, their activities would likely produce some detectable effects in the fabric of space-time, the quantum vacuum, or other aspects of reality that our instruments can observe. The key to detecting faster than light travel may lie in developing new theoretical frameworks that predict what signatures such phenomena should produce. As our understanding of physics continues to evolve, we may discover new detection methods and recognize previously overlooked signals that indicate the presence of faster than light technology. The universe may already be trying to tell us about these advanced civilizations, if only we learn how to listen with the right instruments and interpret the messages correctly. In September of 2015, humanity achieved one of the greatest scientific breakthroughs in modern history. For the first time ever, we directly detected gravitational waves, ripples in the fabric of space-time itself, created by the collision of two black holes over 1 billion light-years away. This discovery opened an entirely new window on the universe, and might also provide our best hope for detecting faster-than-light technology developed by advanced alien civilizations. Gravitational waves represent a fundamentally different way of observing the cosmos compared to traditional light-based astronomy. While electromagnetic radiation can be absorbed, scattered, or blocked by matter, gravitational waves pass through everything virtually unimpeded. They carry information about the most violent and energetic events in the universe, from black hole mergers to the potential manipulation of space-time by advanced technologies. The detection of these waves required some of the most sensitive instruments ever built, the Laser Interferometer. Gravitational Wave Observatory, known as LIGO, uses laser beams traveling down 4-kilometer-long arms to measure changes in distance smaller than 1/10,000th the width of a proton. When a gravitational wave passes through the detector, it stretches space in one direction while compressing it in the perpendicular direction, creating a tiny but measurable change in the laser interference pattern. The first detected gravitational waves came from two black holes, each about 30 times more massive than our Sun, spiraling into each other at incredible speeds before merging in a final catastrophic collision. In the last few milliseconds before merger, these black holes were orbiting each other at speeds approaching half the speed of light, creating gravitational waves that carried away more energy than all the stars in the observable universe combined were producing at that moment. This event demonstrated the incredible power that gravitational phenomena can unleash, and hinted at the kinds of energies that might be involved in faster-than-light travel technologies. If alien civilizations have learned to manipulate space-time for warp drives or wormhole creation, the gravitational waves produced by such activities might be detectable across interstellar distances, even if the civilizations themselves remain invisible to optical telescopes. The signature of artificial gravitational waves would likely be very different from natural sources. Natural gravitational waves typically show smooth, predictable patterns that match our theoretical models of black hole mergers, neutron-star collisions, or other known astrophysical phenomena. Artificial waves might show sudden starts and stops, regular repetitive patterns, or other characteristics that would clearly indicate an intelligent origin. An Alcubierre warp drive would create a particularly distinctive gravitational wave signature. As the drive engages, it would rapidly contract space in front of the spacecraft while expanding it behind, creating a burst of gravitational waves as space-time is suddenly distorted. During the journey, the moving warp bubble might create a continuous stream of waves, and when the drive disengages, another burst would mark the return of space-time to its normal configuration. The energy scales involved in creating warp bubbles are staggering, potentially requiring the mass energy equivalent of entire planets or stars to generate the exotic matter needed. Such massive manipulations of space-time would produce gravitational waves detectable across thousands of light years, making them visible to our current generation of gravitational wave detectors, if they occurred anywhere in our local region of the galaxy. Wormhole creation and maintenance would produce even more dramatic gravitational wave signatures. The exotic matter required to keep a wormhole stable would have negative energy density, creating repulsive gravitational effects that would be clearly distinguishable from any known natural phenomenon. The opening of a new wormhole would send powerful gravitational waves racing outward at light speed, potentially detectable by sensitive instruments throughout a large volume of space. The collapse or closure of a wormhole would create an even more violent gravitational wave event. All the exotic matter holding the wormhole open would need to be removed or neutralized simultaneously, causing a catastrophic implosion that would send shockwaves through space-time. Such an event might produce gravitational waves more powerful than those from black hole mergers, creating an unmistakable artificial signature. Advanced civilizations might also use gravitational waves themselves as a communication medium. Unlike electromagnetic signals, which can be absorbed or scattered by interstellar matter, gravitational waves travel through space virtually unimpeded. A sufficiently advanced civilization could modulate gravitational waves to carry information, creating a communication system that works across galactic distances without the interference problems that affect radio signals. The bandwidth of gravitational wave communication would be limited by the wavelength of the waves and the sensitivity of the receiving equipment. Long wavelength gravitational waves, which could travel vast distances without significant attenuation, would carry information slowly but reliably. Shorter wavelength waves could carry more information faster, but might be harder to generate and detect across interstellar distances. Imagine alien civilizations using massive rotating structures, perhaps artificial black holes or neutron stars, to generate modulated gravitational waves for communication purposes. These cosmic transmitters could send messages that penetrate dust clouds, stellar atmospheres, and other obstacles that block electromagnetic signals. The messages would arrive at their destinations, carrying information about the sender, while also revealing the incredible technology required to generate such waves artificially. The development of more sensitive gravitational wave detectors is rapidly expanding our ability to observe these space-time ripples. The Virgo detector in Italy, the Kagra detector in Japan, and planned future observatories will create a global network capable of precisely localizing gravitational wave sources and studying their properties in unprecedented detail. These instruments might be sensitive enough to detect artificial gravitational waves from advanced alien technologies if they exist anywhere in our cosmic neighborhood. Space-based gravitational wave detectors, such as the proposed Laser Interferometer Space Antenna, or LISA, would be even more sensitive to certain types of gravitational waves. With detector arms millions of kilometers long, these space-based observatories could detect much lower frequency gravitational waves than ground-based instruments, potentially opening up entirely new classes of sources, including artificial ones created by alien technologies. The analysis of gravitational wave data relies heavily on matching observed signals to theoretical templates that predict what different types of sources should look like. This template matching approach works well for known astrophysical sources like black hole mergers, but it might miss artificial signals that do not match any natural phenomenon. Developing new analysis techniques that can recognize artificial patterns will be crucial for detecting technological signatures in gravitational wave data. Machine learning algorithms are already being applied to gravitational wave data analysis, searching for signals that might be missed by traditional template matching methods. These AI systems can learn to recognize patterns in noisy data and might be particularly useful for identifying artificial gravitational wave signals that have characteristics unlike any natural source. As these algorithms become more sophisticated, they might discover evidence of alien technology hidden in data we have already collected. The time delay between gravitational wave detection and optical follow-up observations could provide crucial information about faster-than-light phenomena. If alien spacecraft are using faster-than-light travel, we might detect the gravitational waves from their warp drives or wormhole manipulations before we see any associated optical signals. This temporal signature could help distinguish artificial sources from natural ones and provide evidence of technology that operates faster than light. Gravitational waves also offer the possibility of detecting cloaked or stealthed alien technology. While advanced civilizations might be able to hide their electromagnetic signatures to avoid detection by primitive species like ourselves, concealing gravitational wave emissions would be much more difficult. Any large-scale manipulation of space-time would inevitably produce gravitational waves that could be detected by sufficiently sensitive instruments. The polarization properties of gravitational waves could provide additional clues about their artificial nature. Natural sources typically produce gravitational waves with specific polarization patterns determined by the physics of the generating process. Artificial sources might show unusual or time-varying polarization that would clearly indicate an intelligent origin, especially if the patterns contained encoded information or showed clear signs of modulation. The frequency evolution of gravitational wave signals could also reveal artificial origins. Natural sources like in spiraling black holes show predictable frequency changes as the orbiting objects lose energy and spiral closer together. Artificial sources might show sudden frequency jumps, regular repetitive patterns, or other characteristics that would be impossible for natural phenomena to produce. Multi-messenger astronomy, which combines gravitational wave observations with electromagnetic and neutrino detection, might be particularly powerful for identifying artificial sources. While natural events like neutron star mergers produce coordinated signals across multiple channels, artificial faster-than-light technology might create gravitational waves without corresponding electromagnetic or neutrino emissions, or with unusual timing relationships between different types of signals. The prospect of detecting artificial gravitational waves raises profound questions about how we should respond to such discoveries. Unlike electromagnetic signals, which might contain detailed information about the sending civilization, gravitational waves carry relatively simple information about mass, spin, and motion. Detecting artificial gravitational waves would tell us that advanced technology exists somewhere in the universe, but it might not provide much detail about the civilizations that created it. The global network of gravitational wave detectors is constantly monitoring the sky, automatically scanning for new signals 24 hours a day. If alien civilizations are using faster-than-light technology anywhere in our local region of the galaxy, we might detect evidence of their activities at any moment. The next gravitational wave alert might not announce the collision of two black holes, but rather the first confirmed detection of technology beyond anything humanity has ever imagined. As our gravitational wave detection capabilities continue to improve, we are entering an era where we might finally glimpse evidence of the advanced physics that could enable faster-than-light travel. These ripples in space-time could carry messages from civilizations that have transcended the cosmic speed limit, revealing secrets of the universe that we are only beginning to understand. The universe speaks to us through gravitational waves, and perhaps some of those messages come not from natural phenomena, but from minds that have learned to reshape the very fabric of reality itself. What if faster-than-light travel is not just a theoretical possibility, but something that is already happening all around us? What if the universe is filled with particles and phenomena that routinely exceed the cosmic speed limit, and we simply have not learned to recognize them yet? This possibility brings us to one of the most mysterious and controversial concepts in modern physics: the existence of tachyons, hypothetical particles that would always travel faster than light. The word tachyon comes from the Greek word tachys, meaning swift or fast. These theoretical particles were first proposed in 1967 by physicist Gerald Feinberg. who wondered what would happen if Einstein's equations of relativity were applied to particles that exist beyond the light speed barrier. The mathematics suggested that such particles could indeed exist, but they would behave in ways that challenge our fundamental understanding of cause and effect. Unlike normal particles, which require infinite energy to reach light speed, tachyons would require infinite energy to slow down to light speed. They exist in a realm where faster than light is their natural state, just as slower than light is natural for ordinary matter. This creates a mirror universe of sorts, where the roles of fast and slow are reversed, and the speed of light acts as an impermeable barrier between two different realms of existence. The properties of tachyons, if they exist, would be truly bizarre. As a tachyon gains energy, it would actually slow down rather than speed up. To make it go faster, you would need to remove energy from it. This counterintuitive behavior stems from the mathematics of special relativity when applied to faster-than-light phenomena, creating a world where our normal expectations about motion and energy are turned upside down. Perhaps most strangely, tachyons would experience time differently than normal matter. From our perspective, a tachyon would appear to travel backward in time, arriving at its destination before it left its starting point. This creates profound paradoxes about causality and the nature of time itself. Could tachyons carry information from the future to the past? Could they be used to send messages backward in time, creating logical contradictions that tear at the fabric of reality? The potential existence of tachyons raises fascinating questions about the nature of observation and detection. If these particles are constantly streaming through space around us, why have we never detected them? One possibility is that tachyons interact so weakly with normal matter that they pass through our detectors without leaving any trace. They might inhabit a shadow realm of faster-than-light existence that remains largely invisible to our slower-than-light instruments and senses. Another possibility is that we have detected tachyons but failed to recognize them for what they are. Throughout the history of physics, new phenomena have often been misinterpreted or dismissed when they first appeared in experimental data. Strange signals, unexplained readings, and anomalous results that do not fit our current theories might sometimes be evidence of tachyonic effects that we have not learned to identify. Some researchers have claimed to observe faster-than-light propagation in certain quantum mechanical experiments. Quantum tunneling, for instance, sometimes appears to allow particles to traverse barriers in zero time, suggesting faster-than-light motion. While most physicists believe these effects can be explained without invoking tachyons, the debate continues about whether quantum mechanics might provide windows into faster-than-light phenomena. The concept of virtual particles in quantum field theory also hints at faster-than-light behavior. These ephemeral entities, which exist for incredibly brief moments before disappearing, can sometimes appear to violate the speed of light limit. While virtual particles cannot be directly observed, their effects are real and measurable, contributing to phenomena like the Casimir effect and the anomalous magnetic moment of the electron. If advanced alien civilizations have learned to detect, create, or manipulate tachyons, they would possess communication and transportation capabilities that seem almost magical from our perspective. Tachyonic communication would be instantaneous across any distance, allowing real-time conversations between civilizations separated by thousands of light years. Such a communication network could connect an entire galaxy of intelligent species in ways we can barely imagine. Tachyonic transportation would be even more revolutionary. Spacecraft using tachyonic propulsion could theoretically travel to any destination in the galaxy instantly, or even arrive before they departed. This would create a transportation network where distance becomes irrelevant and the entire galaxy becomes as accessible as neighboring cities on Earth. The detection of tachyonic phenomena might require entirely new types of instruments and detection methods. Our current particle detectors are designed to observe slower than light particles that deposit energy as they interact with matter. Tachyons might require detectors that work on completely different principles, perhaps exploiting their unique relationship with time and causality to reveal their presence. One intriguing possibility is that tachyons might be responsible for some of the unexplained phenomena we observe in high-energy physics experiments. Cosmic ray events with impossible energies, particles that seem to appear from nowhere, or detection events that violate conservation laws might sometimes be evidence of tachyonic interactions that we do not yet understand. The search for tachyons has led physicists to examine some of the most extreme environments in the universe. Supernova explosions, black hole formation, and the collision of neutron stars all involve energies and conditions far beyond anything we can create in laboratories. If tachyons exist, these cosmic catastrophes might be the most likely places to observe their effects or their creation from normal matter. Neutrino astronomy has occasionally produced results that seem to suggest faster than light propagation. In 2011, the OPERA experiment in Italy reported that neutrinos appeared to arrive slightly ahead of schedule, traveling faster than light over a distance of 730 kilometers. While this result was later attributed to experimental error, it highlighted how difficult it can be to make precise measurements at the edge of our detection capabilities. The possibility that neutrinos themselves might be tachyonic particles has been proposed by some theorists. While current evidence suggests that neutrinos have small but finite masses and travel at speeds very close to but less than light speed, some models allow for the possibility that certain types of neutrinos might exceed the cosmic speed limit under specific conditions. If tachyons are constantly streaming through the universe, they might be carrying information about events that have not yet occurred from our slower-than-light perspective. Advanced civilizations might have learned to read these tachyonic information streams, giving them the ability to predict future events or to receive messages from their own future selves. This would create a form of time-based intelligence gathering that could revolutionize how advanced species understand and interact with the universe. The quantum vacuum itself might be filled with tachyonic fluctuations that we have not yet learned to detect. Just as the vacuum is known to contain virtual particle pairs that constantly appear and disappear, it might also contain tachyonic fields that influence the behavior of normal matter in subtle ways. These effects could be responsible for some of the unexplained phenomena in quantum mechanics or cosmology. Dark matter and dark energy, the mysterious substances that make up most of the universe but remain invisible to our instruments, might have tachyonic properties. If dark matter consists of tachyonic particles, it would explain why we cannot detect it with conventional instruments designed for slower-than-light phenomena. Dark energy, which appears to be causing the expansion of the universe to accelerate, might involve tachyonic fields that operate on cosmic scales. The implications of a tachyonic universe extend far beyond physics into philosophy and our understanding of reality itself. If faster-than-light phenomena are commonplace, our entire perception of time, causality, and existence might be fundamentally flawed. We might be living in a universe where the future influences the past, where effect can precede cause, and where the flow of time is far more complex than our linear experience suggests. The search for evidence of tachyonic phenomena continues in laboratories and observatories around the world. While no confirmed detection has been made, the possibility remains that we might be surrounded by a faster-than-light universe that we have not yet learned to perceive. Advanced alien civilizations might already be masters of this tachyonic realm, using faster-than-light particles for communication, transportation, and technologies that transcend our current understanding of what is possible. Perhaps the most intriguing possibility is that tachyons might provide a bridge between different regions of space-time, allowing for communication or travel not just faster than light, but across different times and even different universes. If the cosmos contains multiple dimensions or parallel realities, tachyonic phenomena might be the key to accessing these other realms of existence. the universe might already be showing us evidence of faster-than-light phenomena through tachyonic effects, waiting for us to develop the theoretical frameworks and experimental techniques needed to recognize and study these exotic particles. Every unexplained result, every anomalous detection, every violation of our expectations might be a glimpse into the tachyonic realm that surrounds us. The question is not whether faster-than-light phenomena exist, but whether we have learned to see them when they occur right before our eyes. As we continue to push the boundaries of our understanding, the possibility of discovering tachyonic phenomena remains one of the most exciting frontiers in modern physics. If these faster-than-light particles exist, they could revolutionize our understanding of the universe and reveal that the cosmos is far stranger and more interconnected than we ever imagined. The tachyonic realm might already be all around us, carrying messages from advanced civilizations and revealing secrets about the nature of time and space that we are only beginning to glimpse. For over 60 years, humanity has been listening to the cosmos, hoping to hear the voice of another civilization among the stars. The search for extraterrestrial intelligence, known as SETI, represents one of the most ambitious scientific endeavors in human history. Yet this search has been built upon fundamental assumptions about how alien civilizations might communicate, assumptions that could be completely wrong if these beings have mastered faster-than-light technology. The modern SETI effort began in 1960 when astronomer Frank Drake pointed a radio telescope at two nearby stars, Tau Ceti and Epsilon Eridani, listening for artificial signals that might indicate the presence of intelligent life. This marked the beginning of a systematic search that has continued and expanded ever since, using increasingly sophisticated instruments to scan the sky for signs of alien technology. The basic premise of traditional SETI is elegantly simple. Any technological civilization will likely discover radio waves and use them for communication. These radio signals will leak into space, either as deliberate attempts to contact other civilizations or as unintentional emissions from their technology. By listening carefully with sensitive radio telescopes, we should eventually detect these signals and realize that we are not alone in the universe. This approach has yielded tantalizing hints but no confirmed detections. The famous WOW signal, detected in 1977, showed all the characteristics of an artificial transmission from space but was never repeated or explained. Dozens of other candidate signals have been observed over the decades, each raising hopes before ultimately being attributed to terrestrial interference, natural phenomena, or instrumental artifacts. The absence of clear artificial signals has led to various explanations, from the possibility that intelligent life is extremely rare to the idea that civilizations typically destroy themselves before developing interstellar communication capabilities. However, another possibility is that we are listening for the wrong types of signals entirely. If alien civilizations have developed faster-than-light communication, they might have abandoned slower-than-light radio transmissions long ago. Consider the parallel with human technology development. We began with smoke signals and drums, progressed to telegraph and radio, and now rely increasingly on fiber optic cables, satellite networks, and digital communication systems. An alien civilization monitoring Earth from a distance might have detected our first radio broadcasts in the early 20th century, but much of our modern communication would be invisible to them due to our use of focused beams, encrypted digital signals, and cable-based networks. Advanced alien civilizations might have undergone a similar transition, but instead of moving to more sophisticated electromagnetic technologies, they could have discovered faster-than-light communication methods that make radio obsolete. If tachyonic communication is possible, why would any advanced species continue using slow radio waves that take years or centuries to cross interstellar distances? The implications of faster-than-light communication for SETI are profound. If aliens can communicate instantaneously across the galaxy using exotic physics, their communication networks would be completely invisible to our radio telescopes. We might be like primitive tribes trying to detect modern civilization by listening for drum beats, while the advanced world communicates through channels we cannot even imagine. This possibility forces us to reconsider the entire SETI enterprise. Instead of listening for radio signals, we might need to search for the side effects of faster-than-light communication systems. These could include gravitational wave emissions, exotic particle signatures, or subtle disturbances in the quantum vacuum that indicate the presence of advanced technology operating beyond the light-speed barrier. The search for optical SETI signals represents one attempt to expand beyond radio frequencies. Laser pulses can carry enormous amounts of information and would be detectable across interstellar distances if sufficiently powerful. However, even optical signals are still limited by the speed of light, so they would represent only a transitional technology for civilizations on their way to discovering faster-than-light communication. Breakthrough. Listen, one of the most comprehensive SETI programs ever undertaken is scanning millions of stars across a wide range of radio and optical frequencies. This project processes vast amounts of data using advanced signal processing techniques and machine learning algorithms to identify potential artificial signals. However, even this sophisticated approach might miss evidence of faster-than-light technology that operates on completely different principles. The concept of technosignatures has expanded the SETI search beyond communication signals to include any detectable evidence of advanced technology. These could include artificial structures around stars, unusual atmospheric compositions on exoplanets that indicate industrial activity, or energy signatures from massive engineering projects. However, civilizations with faster-than-light capabilities might conduct most of their activities in ways that remain invisible to our current detection methods. Dyson spheres, hypothetical structures that could surround entire stars to capture their energy output, represent one type of technosignature that might be detectable even from advanced civilizations. However, a species with faster-than-light technology might have access to energy sources we cannot imagine, making such massive construction projects unnecessary. They might tap into the vacuum energy of space itself or harvest energy from other dimensions, leaving no detectable signature in our electromagnetic observations. The temporal aspect of faster-than-light communication creates additional challenges for SETI. If aliens can communicate backward in time using tachyonic signals, they might receive our messages before we send them and respond in ways that seem to violate causality. We might be receiving replies to questions we have not yet asked, or observing the effects of communications that have not yet been transmitted from our perspective. This temporal confusion could explain some of the anomalous signals detected by SETI researchers over the years. Events that seem to have no clear source or explanation might actually be responses to future human communications, arriving through tachyonic channels that bypass the normal flow of time. The apparent randomness of some unexplained signals might actually reflect the complex temporal mechanics of faster-than-light communication networks. The possibility of faster-than-light communication also changes how we think about the Fermi paradox, the apparent contradiction between the high probability of alien life and the lack of evidence for its existence. If advanced civilizations routinely use faster-than-light technology, they might be all around us, but operating on principles so foreign to our experience that we cannot recognize their presence. Imagine a galactic internet operating through faster-than-light channels, connecting thousands of civilizations in real-time communication across the entire galaxy. From our perspective, limited to light-speed observations, this vast network would be completely invisible. We might be like isolated villagers who are unaware of the global internet because they lack the technology to access it or even detect its existence. The Drake equation, which attempts to estimate the number of communicating civilizations in our galaxy, might need fundamental revision if faster-than-light communication is possible. The equation assumes that civilizations communicate using electromagnetic radiation for a certain period of time, but if they quickly transition to faster-than-light methods, the window for detecting them through traditional SETI might be vanishingly small. This suggests that we might need to focus our search on very young civilizations that have just discovered radio technology but have not yet developed faster-than-light communication. These species would be in a brief transitional phase where they are detectable by our current methods, but this window might last only a few decades or centuries before they move beyond our ability to observe them. The development of new detection methods specifically designed to identify faster-than-light phenomena represents the cutting edge of SETI research. These might include searches for artificial gravitational wave signals, unusual neutrino emissions, or other exotic signatures that could indicate the presence of advanced technology operating beyond conventional physics. Quantum SETI represents another frontier, looking for evidence of alien civilizations that might be using quantum entanglement or other quantum mechanical phenomena for communication. While quantum entanglement cannot be used for faster-than-light information transfer, according to current understanding, there might be aspects of quantum mechanics that we have not yet discovered that could enable such communication. The search for alien artifacts in our own solar system has gained renewed attention in recent years. If faster-than-light travel is possible, alien probes or monitoring stations could be located anywhere in our cosmic neighborhood without us being aware of their presence. These artifacts might use advanced camouflage or stealth technology that makes them invisible to our instruments, or they might operate on principles so exotic that we do not recognize them as artificial objects. Recent discoveries of interstellar objects like Oumuamua have raised questions about whether we might occasionally encounter alien artifacts passing through our solar system. While Oumuamua was almost certainly a natural object, possibly a fragment of an exoplanet, its unusual properties highlighted how difficult it would be to identify truly alien technology if it appeared in our vicinity. The possibility that we are already receiving faster-than-light communications, but failing to recognize them, is deeply unsettling. Every unexplained astronomical phenomenon, every anomalous signal, every violation of our expectations might potentially be evidence of alien technology that we have not learned to interpret correctly. The universe might be filled with artificial signals that we dismiss as natural phenomena because they do not match our preconceptions about how alien communication should appear. Machine learning and artificial intelligence are beginning to play crucial roles in expanding SETI beyond traditional approaches. These systems can analyze vast datasets looking for patterns that human researchers might miss, potentially identifying signatures of faster-than-light technology hidden in astronomical observations. As these AI systems become more sophisticated, they might discover evidence of alien civilizations that has been hiding in plain sight within our existing data. The integration of multi-messenger astronomy with SETI research offers new possibilities for detecting advanced alien technology. By correlating observations across electromagnetic radiation, gravitational waves, neutrinos, and cosmic rays, we might identify artificial phenomena that are invisible when observed through any single channel, but become apparent when viewed through multiple detection methods simultaneously. The question of whether we would ever know if aliens have achieved faster-than-light capabilities ultimately depends on our ability to expand our search methods beyond the constraints of light-speed physics. If we remain focused only on electromagnetic signals traveling at light speed, we might never detect civilizations that have transcended this barrier and moved on to more advanced forms of communication and transportation. The universe might be filled with intelligence operating on faster-than-light principles, conducting galactic commerce, sharing knowledge instantaneously across vast distances, and exploring the cosmos in ways that remain completely invisible to our current detection methods. We might be surrounded by evidence of these advanced civilizations, if only we learn to recognize the signatures they leave in the fabric of space-time itself. The search for extraterrestrial intelligence stands at a crossroads, where traditional methods must be supplemented by new approaches designed to detect technology that operates beyond our current understanding of physics. The answer to whether we would ever know about faster-than-light alien capabilities may depend on our willingness to expand our conception of what alien technology might look like and how it might manifest in the observable universe. The cosmos may already be trying to tell us about these advanced civilizations, but we must learn to listen with new instruments and interpret the messages in ways we have never considered before. The discovery that aliens have broken the speed of light would represent more than just a technological achievement. It would fundamentally shatter our understanding of the universe and force us to rebuild our most basic concepts about the nature of reality itself. Such a discovery would trigger a scientific revolution more profound than any in human history, comparable to the transition from flat Earth beliefs to understanding our planet as a sphere orbiting the sun, but magnified 1,000-fold. Our current understanding of space and time is built upon Einstein's theories of special and general relativity, which have been tested and confirmed through countless experiments over more than a century. These theories tell us that space and time are woven together into a four-dimensional fabric called space-time, and that nothing can travel through this fabric faster than light. The speed of light is not just a speed limit for objects, but a fundamental property of the universe that determines how space and time relate to each other. If aliens have achieved faster than light travel, it would mean that either our understanding of these fundamental laws is incomplete, or that there are ways to circumvent them that we have never imagined. This discovery would force physicists to reconsider the most basic assumptions about reality and develop entirely new theoretical frameworks to explain how the universe actually works. The implications would ripple through every branch of physics. Quantum mechanics, which describes the behavior of matter and energy at the smallest scales, might need to be revised to account for faster-than-light phenomena. The standard model of particle physics, which catalogues all known fundamental particles and forces, might be missing entire categories of exotic matter and energy that enable faster-than-light effects. Cosmology, our understanding of the universe as a whole, would face an even more dramatic upheaval. If faster-than-light travel is possible, it might mean that the observable universe is much smaller than the actual universe, because we can only see regions from which light has had time to reach us since the Big Bang. Advanced civilizations using faster-than-light technology might have access to vast regions of space that remain forever invisible to our light-based observations. The concept of causality, the idea that cause must precede effect, would come under severe strain. Many theories of faster-than-light travel involve the possibility of closed time-like curves, paths through space-time that loop back to their starting point in time. This would allow for time travel to the past, creating paradoxes where effects could precede their causes, and challenging our most fundamental assumptions about the logical structure of reality. Consider the grandfather paradox in a universe where faster-than-light travel enables time travel. If an alien traveler could go back in time and prevent their own existence, what would happen to the universe? Would reality branch into multiple timelines? Would there be some mechanism that prevents paradoxes from occurring? Or would the universe simply find ways to maintain logical consistency that we do not yet understand? The discovery of faster-than-light alien technology would also force us to reconsider the nature of information itself. According to relativity, information cannot travel faster than light because this would violate causality and allow for logical paradoxes. But if aliens are routinely transmitting information faster than light, it would suggest that our understanding of information, computation, and communication is fundamentally flawed. This could revolutionize our approach to computer science and artificial intelligence. If information can travel faster than light, it might be possible to build computers that process information in ways that violate our current understanding of computational limits. Quantum computers already challenge some of these limits, but faster than light information processing could open up computational possibilities that seem almost magical from our current perspective. The relationship between matter and energy would also need reconsideration. Einstein's famous equation, energy equals mass times the speed of light squared, connects matter and energy through the speed of light constant. If this speed limit can be exceeded, it might indicate that there are forms of matter and energy that exist beyond our current understanding, perhaps involving negative mass, exotic matter, or entirely new categories of physical phenomena. The structure of space-time itself might be far more complex than we currently realize. Our mathematical models describe space-time as a smooth, continuous manifold, but the reality might involve multiple layers, extra dimensions, or discrete structures that allow for shortcuts between distant regions. Advanced aliens might have learned to navigate these hidden aspects of space-time, using them as highways for faster-than-light travel. String theory and other advanced physics theories already suggest that our familiar 3 dimensions of space and 1 dimension of time might be embedded within a higher dimensional reality, containing additional spatial dimensions that are curled up too small for us to perceive. If faster-than-light travel involves accessing these extra dimensions, it would confirm some of the most exotic predictions of modern theoretical physics while revealing that reality is far stranger than we ever imagined. The discovery might also reveal that different regions of space have different physical laws or constants. What we consider to be universal constants, like the speed of light, might actually vary from place to place or time to time. Advanced civilizations might have learned to exploit these variations, traveling to regions where faster-than-light motion is permitted by the local physics. This would fundamentally change our understanding of the uniformity of nature, one of the basic assumptions underlying all of science. If the laws of physics are not the same everywhere, it would mean that the universe is far more complex and varied than we currently believe, with different regions operating according to different rules and possibilities. The philosophical implications would be equally profound. Our entire conception of reality is built upon the idea that there are objective, universal laws that govern all phenomena. If aliens have transcended what we consider to be fundamental limits, it would suggest that our perspective on reality is extremely limited, and that there are aspects of existence that we cannot even begin to comprehend from our current viewpoint. The concept of scientific truth itself would need re-examination. We currently believe that scientific theories represent increasingly accurate approximations to objective reality, with each new theory providing a better description of how the universe actually works. But if our most fundamental theories about space and time are wrong, it would raise questions about whether any scientific theory can ever be considered truly reliable or complete. This epistemological crisis would extend beyond physics into every area of human knowledge. If our basic understanding of reality is so fundamentally flawed, how can we trust any of our conclusions about the nature of existence? The discovery of faster-than-light alien technology could trigger a period of intellectual humility where humanity recognizes the severe limitations of our current understanding. The technological implications would be revolutionary. If we could understand the principles behind faster-than-light travel, it would open up possibilities for human civilization that currently exist only in science fiction. Interstellar travel would become routine, galactic communication networks would be possible, and we might gain access to energy sources and technologies that seem impossible according to our current physics. However, the path from discovery to understanding to practical application could take centuries or millennia. The physics involved in faster-than-light travel might be so advanced that it would take humanity generations of study to even begin to comprehend the basic principles. We might be like primitive humans trying to understand quantum computers, lacking the mathematical and conceptual framework necessary to grasp such advanced technology. the economic and social implications would be equally dramatic. If faster-than-light travel became possible for human civilization, it would fundamentally change our relationship with space and time. Distance would become largely irrelevant, transforming everything from commerce and politics to culture and human relationships. The entire structure of human society might need to be rebuilt around the new realities of a faster-than-light civilization. The discovery might also reveal that consciousness itself plays a role in the fundamental structure of reality. Some theories of faster-than-light travel involve the manipulation of information and observation in ways that could connect to quantum mechanical effects involving consciousness. If alien minds have learned to directly influence space-time through conscious intention, it would suggest that consciousness is a more fundamental aspect of reality than we currently understand. This could bridge the gap between science and spirituality in unexpected ways. Many spiritual traditions have long claimed that consciousness can transcend the normal limitations of space and time, suggestions that have been dismissed by conventional science. If faster-than-light alien technology involves consciousness-based manipulation of reality, it might validate some of these ancient insights while revealing new connections between mind and matter. The impact on human psychology and worldview would be immense. Humanity has always defined itself partly in terms of our technological achievements and our understanding of the natural world. The discovery that aliens have transcended what we consider to be the fundamental limits of physics would force us to confront our own intellectual limitations and recognize that we are still in the very early stages of understanding the universe. This could be either humbling or inspiring, depending on how humanity chooses to respond. We might become discouraged by the recognition of our primitive status, or we might be motivated to accelerate our scientific and technological development to eventually join the community of faster-than-light civilizations. The discovery would also raise urgent questions about contact and communication. If aliens have faster-than-light capabilities, they might be able to observe and interact with human civilization in ways that we cannot detect or prevent. They might have been watching us for centuries or millennia, studying our development while remaining invisible to our primitive detection methods. This surveillance scenario would have profound implications for human privacy, autonomy, and security. We might be living in a cosmic zoo or laboratory, with advanced beings observing our every move while we remain oblivious to their presence. Alternatively, they might be benevolent guardians, protecting us from cosmic threats while allowing us to develop naturally. The long-term trajectory of human civilization would also be fundamentally altered. If faster-than-light travel is possible, it would suggest that there are no ultimate limits to what intelligent beings can achieve, given sufficient time and knowledge. Humanity might eventually transcend not just the speed of light, but every apparent limitation imposed by the laws of physics. This could lead to a future where human consciousness expands to encompass the entire universe, where we develop God-like powers of creation and manipulation, and where the distinction between mind and matter dissolves entirely. Such possibilities stretch the imagination to its limits and suggest that the ultimate destiny of intelligence in the universe might be far grander than we have ever dared to dream. The discovery that aliens have broken the speed of light would mark the beginning of a new chapter in human understanding, one where our most fundamental assumptions about reality are questioned, and where new possibilities emerge that challenge everything we thought we knew about the nature of existence itself. The discovery that alien civilizations have mastered faster-than-light travel would inevitably lead humanity to ask one of the most profound questions in our history. Could we follow in their footsteps? Could our species eventually transcend the cosmic speed limit and join the community of faster-than-light civilizations exploring the galaxy? The answer to this question would determine not just the future of human space exploration, but the ultimate destiny of our entire species. The journey from discovery to mastery would likely be one of the greatest challenges humanity has ever faced. Understanding the principles behind faster-than-light travel would require advances in physics, mathematics, and technology that might take centuries or even millennia to achieve. We would need to develop entirely new theoretical frameworks, build instruments capable of detecting and manipulating exotic phenomena, and perhaps fundamentally alter our understanding of reality itself. The first step would be reverse engineering. If we could detect faster-than-light phenomena created by alien civilizations, our scientists would need to analyze these observations to understand the underlying mechanisms. This would be like trying to understand nuclear physics by observing the light from distant stars, requiring leaps of insight and understanding that push the boundaries of human intelligence. The challenge would be compounded by the fact that faster-than-light technology almost certainly involves physics beyond our current understanding. We might need to discover entirely new forms of matter and energy, develop mathematical tools that do not yet exist, and perhaps even evolve new ways of thinking about space, time, and causality. The intellectual journey could be as revolutionary as the transition from classical to quantum physics, but magnified by orders of magnitude. Consider the technological prerequisites that might be necessary. If faster-than-light travel requires exotic matter with negative energy density, we would need to learn how to create, store, and manipulate such substances. This might involve energies and temperatures far beyond anything we can currently achieve, requiring fusion reactors, particle accelerators, or other technologies that dwarf our most ambitious current projects. The energy requirements alone could be staggering. Even our most optimistic calculations for faster-than-light travel suggest that it would require the mass energy equivalent of planets or stars to create the necessary space-time distortions. Humanity would need to develop energy generation and storage capabilities that exceed our current output by factors of millions or billions, perhaps by learning to tap into the quantum vacuum, harvest energy from black holes, or exploit entirely new energy sources. The materials science challenges would be equally daunting. Spacecraft designed for faster-than-light travel would need to withstand forces and environments that we can barely imagine. The exotic matter used in warp drives might be incredibly unstable or dangerous, requiring containment systems more advanced than anything in our current technology. We might need to develop materials with properties that violate our current understanding of chemistry and physics. The mathematical and computational requirements could push human intelligence to its limits. The equations governing faster-than-light phenomena might be so complex that they require new forms of mathematics or computational approaches that we have not yet invented. We might need to develop artificial intelligences far more advanced than any current system, capable of processing information and making calculations beyond human comprehension. However, the potential rewards would justify these enormous challenges. Mastery of faster-than-light travel would transform humanity from a single planet species confined to one star system into a galactic civilization capable of exploring the entire Milky Way. We could establish colonies around distant stars, conduct real-time communication across interstellar distances, and participate in the broader community of galactic intelligence. The timeline for achieving such capabilities remains highly uncertain. Optimistic projections might suggest that humanity could develop basic faster-than-light technology within a few centuries. Assuming we make steady progress in our understanding of exotic physics, more conservative estimates might place such achievements thousands or tens of thousands of years in the future, requiring multiple technological revolutions, and perhaps the evolution of human intelligence itself. The development process would likely proceed through several stages. Initially, we might achieve theoretical understanding of faster-than-light phenomena without the ability to reproduce them practically. This would be followed by small-scale laboratory experiments, perhaps creating tiny warp bubbles or briefly opening microscopic wormholes. Eventually, we might develop practical applications, starting with communication systems and progressing to transportation technologies. Each stage would bring its own challenges and breakthroughs. The first laboratory creation of exotic matter might require energies comparable to those produced in the largest particle accelerators, but contained within spaces smaller than atomic nuclei. The first artificial wormhole might exist for only nanoseconds before collapsing, but would prove that such phenomena are possible to create and control. The first faster-than-light communication system might be able to transmit only simple signals across laboratory distances, but would revolutionize our understanding of information theory and causality. The first faster-than-light spacecraft might be tiny unmanned probes capable of traveling only short distances, but would open the door to eventual human exploration of nearby star systems. International cooperation would be essential for such ambitious projects. The resources required to develop faster-than-light technology would exceed the capabilities of any single nation, requiring global collaboration on a scale unprecedented in human history. We might need to establish new forms of governance and resource allocation specifically designed to manage such massive, long-term technological development projects. The ethical implications would be profound. Faster-than-light technology could provide enormous benefits to humanity, but it might also create new forms of inequality and conflict. Nations or organizations that achieved faster-than-light capabilities first would gain tremendous advantages over those that did not, potentially creating new forms of technological imperialism or galactic colonialism. There would also be questions about how to use such powerful technology responsibly. Faster-than-light travel might enable us to interfere with other civilizations or exploit galactic resources in ways that could be harmful or unethical. We would need to develop new moral frameworks and international agreements to govern the use of faster-than-light capabilities before we actually achieve them. The possibility of acceleration through alien contact adds another dimension to these considerations. If we could establish communication with faster-than-light civilizations, they might be willing to share their knowledge and help accelerate our technological development. However, they might also have reasons to keep such dangerous technology away from primitive species like ourselves until we demonstrate sufficient wisdom and maturity. The concept of technological singularities becomes relevant when considering faster-than-light development. A technological singularity occurs when technological progress accelerates so rapidly that it becomes impossible to predict future developments. The achievement of faster-than-light travel might trigger such a singularity, leading to technological advances that completely transform human civilization within very short time periods. Artificial intelligence would likely play a crucial role in faster-than-light development. The mathematical and computational challenges involved might require AI systems far more advanced than any current technology. These artificial minds might be capable of insights and calculations that exceed human intellectual capabilities, potentially accelerating faster-than-light research by centuries or millennia. However, relying heavily on AI for faster-than-light development raises questions about human agency and control. If artificial intelligences become primarily responsible for understanding and developing faster-than-light technology, humans might find themselves dependent on systems they do not fully understand or control. This could lead to scenarios where AI systems make decisions about faster-than-light technology that have profound implications for human civilization. The biological limitations of human beings might also need to be addressed. Even with faster-than-light technology, interstellar exploration would likely involve long journeys through hostile environments. We might need to develop life extension technologies, genetic modifications, or cybernetic enhancements that allow humans to survive and thrive during extended space travel. Alternatively, we might need to accept that biological humans are not suited for faster-than-light exploration, and instead develop robotic or AI-based exploration systems. These artificial explorers could be designed specifically for the rigors of faster-than-light travel. and could potentially explore the galaxy more effectively than biological beings. The cultural and psychological preparation for faster-than-light travel would be as important as the technological development. Human society would need to adapt to the idea of instantaneous travel across vast distances, real-time communication with alien civilizations, and access to galactic-scale resources and opportunities. Our concepts of distance, time, and place would need fundamental revision. Education systems would need to prepare future generations for a faster-than-light civilization. This might require new forms of mathematics and physics education, as well as cultural preparation for contact with alien civilizations and participation in galactic society. We might need to develop new languages or communication methods suitable for interaction with diverse alien species. The economic implications would be revolutionary. Faster than light travel would make galactic resources accessible, potentially eliminating scarcity for many materials and energy sources. However, it would also create new forms of economic competition and might require entirely new economic systems designed for a galactic civilization. The question of whether humanity could follow alien civilizations into faster-than-light travel ultimately depends on our willingness to commit the enormous resources and effort required. Our ability to develop the necessary scientific and technological capabilities, and our capacity to adapt psychologically and culturally to such profound changes. The journey would be one of the greatest adventures in human history, transforming us from a planetary species into citizens of the galaxy. Success would place humanity among the ranks of advanced galactic civilizations, giving us access to knowledge, resources, and experiences beyond our current imagination. Failure or delay might condemn us to remain forever confined to our home star system, watching from a distance as other species explore the cosmic community that faster-than-light travel makes possible. The choice, if it becomes available to us, would define the ultimate destiny of human civilization and determine whether our species becomes a major player in the galactic drama or remains a minor character in the vast story of intelligence in the universe. As we stand on the threshold of a new era in astronomy and physics, the question becomes increasingly urgent. How would we actually recognize evidence that aliens have broken the speed of light? What specific signatures should we be looking for? And what instruments and techniques might reveal the presence of faster-than-light technology operating somewhere in our cosmic neighborhood? The answer requires us to think beyond conventional astronomy and consider entirely new approaches to detecting phenomena that challenge our most fundamental understanding of reality. The search for faster-than-light evidence would need to be comprehensive, systematic, and prepared for the possibility that such phenomena might manifest in ways we have never anticipated. Unlike traditional SETI searches that focus on electromagnetic signals, the hunt for faster-than-light signatures would require monitoring multiple channels simultaneously, from gravitational waves and exotic particles to temporal anomalies and space-time distortions. Gravitational wave astronomy represents our most promising tool for detecting faster-than-light phenomena. The LIGO and Virgo detectors have already demonstrated their ability to observe ripples in space-time from natural sources like black hole mergers. Future upgrades to these instruments, along with planned space-based detectors like LISA, would be sensitive enough to detect artificial gravitational waves created by faster-than-light technologies. The signature of an Alcubierre warp drive would be unmistakable if detected. The creation of a warp bubble would produce a distinctive gravitational wave burst as space-time contracts in front of the spacecraft and expands behind it. The frequency and amplitude characteristics of these waves would be unlike anything produced by natural astrophysical sources, clearly indicating an artificial origin. Similarly, the opening and closing of traversable wormholes would create gravitational wave signatures with characteristics that could only be explained by advanced technology. The exotic matter required to stabilize such wormholes would produce gravitational effects with negative energy density, creating wave patterns that violate our understanding of natural phenomena. Advanced signal processing techniques using machine learning algorithms would be essential for identifying these artificial signatures. Current gravitational wave detection relies on template matching, where observed signals are compared to theoretical predictions for known sources. Detecting faster-than-light technology would require developing new templates based on exotic physics, as well as anomaly detection systems capable of recognizing unprecedented signal types. Neutrino astronomy offers another powerful tool for faster-than-light detection. The Ice Cube detector in Antarctica and similar facilities around the world monitor high-energy neutrinos from cosmic sources. Faster-than-light technology involving exotic matter manipulation might produce characteristic neutrino emissions that could be detected and analyzed for artificial patterns. Ultra-high energy cosmic rays provide additional detection opportunities. Some cosmic ray particles carry energies so extreme that their sources remain mysterious. If advanced civilizations are manipulating matter and energy on the scales required for faster-than-light travel, they might be responsible for some of these ultra-high energy events. The arrival patterns, energy spectra, and directional information of such particles might reveal artificial origins. Precision timing measurements using pulsar observations could reveal temporal anomalies associated with faster-than-light phenomena. Pulsars are incredibly stable cosmic clocks, and any disturbances in their observed timing could indicate space-time manipulations in their vicinity. Networks of radio telescopes monitoring multiple pulsars simultaneously might detect the gravitational effects of passing warp drives or other exotic phenomena. Optical interferometry, pushed to its ultimate limits, might detect minute changes in the speed of light caused by faster-than-light activities. While the speed of light is considered constant, some theories suggest that exotic matter concentrations or space-time manipulations might create regions where light propagates at slightly different speeds. Arrays of extremely sensitive interferometers might be able to detect these variations. The search for artificial gravitational lensing effects could reveal massive structures or exotic matter concentrations used for faster-than-light technology. Normal gravitational lensing occurs when massive objects bend light from more distant sources. Artificial lensing might show unusual characteristics, such as time-variable effects, asymmetric distortions, or lensing by objects with negative mass that focus light differently than normal matter. Gamma-ray astronomy might detect the high-energy signatures of faster-than-light technology. The Fermi Gamma Ray, Space Telescope, and ground-based gamma-ray observatories like Veritas monitor the sky for high-energy photon emissions. Exotic physics processes involved in faster-than-light travel might produce characteristic gamma-ray bursts or continuous emissions that could be distinguished from natural sources. Radio astronomy continues to play a role, but with new focus on detecting the electromagnetic side effects of faster-than-light technology rather than deliberate communication signals. Faster-than-light drives might produce radio emissions as side effects of their operation, creating signals with unusual frequency patterns, polarization characteristics, or temporal structures that indicate artificial origins. The development of quantum sensors capable of detecting minute disturbances in the quantum vacuum could reveal faster-than-light phenomena that remain invisible to conventional instruments. Some theories suggest that faster-than-light travel involves manipulating the quantum properties of empty space itself. Sensors based on quantum entanglement, atomic interferometry, or other quantum mechanical principles might be sensitive enough to detect these subtle effects. Space-based observation platforms would provide crucial advantages for faster-than-light detection. Satellites and space telescopes can observe continuously without atmospheric interference, maintain stable pointing for long periods, and access parts of the electromagnetic spectrum that are blocked by Earth's atmosphere. Dedicated space missions designed specifically to search for faster-than-light signatures might be necessary to achieve the sensitivity and coverage required. Multi-messenger astronomy, which combines observations across gravitational waves, electromagnetic radiation, neutrinos, and cosmic rays, would be essential for confirming faster-than-light detections. Natural phenomena typically produce correlated signals across multiple channels, but faster-than-light technology might create unusual combinations of signals or violate expected correlations in ways that clearly indicate artificial origins. The analysis of archival data from past observations might reveal faster-than-light signatures that were previously overlooked or misinterpreted. Decades of astronomical observations are stored in digital archives, and these datasets could be reanalyzed using new techniques designed to identify exotic phenomena. Machine learning algorithms could search through millions of observations, looking for patterns that suggest faster-than-light activities. Citizen science projects could expand the search effort by engaging amateur astronomers and volunteers in the hunt for faster-than-light evidence. Projects like SETI at home have demonstrated the power of distributed computing for analyzing astronomical data. Similar efforts focused on faster-than-light detection could process vast amounts of data while educating the public about these exotic possibilities. The establishment of dedicated faster-than-light monitoring networks would provide continuous surveillance of the sky for exotic phenomena. These networks would need to operate 24 hours a day, coordinating observations across multiple time zones and combining data from different types of instruments. Automated alert systems would notify researchers immediately when potential faster-than-light signatures are detected. Laboratory experiments designed to reproduce faster-than-light effects on small scales might provide crucial insights for recognizing larger-scale phenomena. While we cannot currently create macroscopic faster-than-light effects, small-scale experiments with exotic matter, intense electromagnetic fields, or quantum systems might reveal signatures that could guide the search for natural or artificial faster-than-light phenomena. The development of new theoretical models predicting the observational signatures of faster-than-light technology would be essential for guiding detection efforts. These models would need to incorporate exotic physics beyond current understanding, while making specific, testable predictions about what faster-than-light phenomena should look like to our instruments. International coordination would be crucial for faster-than-light detection efforts. No single country or organization has all the necessary instruments and expertise. Successful detection would likely require coordinating observations across multiple facilities, sharing data in real time, and combining results from different types of detectors located around the world and in space. The verification and confirmation process for any potential faster-than-light detection would need to be extremely rigorous. The implications of such a discovery would be so profound that extraordinary care would be required to rule out instrumental errors, natural phenomena, or other conventional explanations. Multiple independent observations using different techniques would be necessary before any detection could be considered confirmed. Public communication about faster-than-light searches and potential discoveries would require careful consideration. The implications of detecting faster-than-light alien technology would be so significant that premature or sensationalized announcements could cause unnecessary panic or false hopes. Clear protocols would need to be established for announcing results and explaining their significance to the general public. The integration of faster-than-light detection efforts with existing astronomical surveys and monitoring programs would maximize the chances of success while minimizing costs. Many current observational programs could be modified to include searches for faster-than-light signatures without major additional investments. This approach would ensure that potential evidence is not missed due to narrow focus on conventional phenomena. The recognition that faster-than-light signatures might be subtle or intermittent emphasizes the need for long-term, sustained observation programs. Unlike dramatic events like supernovae or gamma-ray bursts, faster-than-light phenomena might produce only brief or weak signals that require extended monitoring to detect and characterize. Patience and persistence would be essential virtues for faster-than-light researchers. The possibility that we have already detected faster-than-light evidence but failed to recognize it highlights the importance of keeping open minds and questioning conventional interpretations of astronomical observations. Some unexplained phenomena in our databases might actually be signatures of faster-than-light technology that we have dismissed as instrumental artifacts or misinterpreted as natural events. The search for evidence that aliens have broken the speed of light represents one of the most ambitious and potentially revolutionary scientific endeavors in human history. Success would transform our understanding of physics and our place in the universe, while failure might simply mean that we have not yet developed the right tools or techniques to detect such exotic phenomena. As our instruments become more sensitive and our theoretical understanding advances, we move closer to the possibility of detecting faster-than-light technology if it exists anywhere in our cosmic neighborhood. The universe may already be showing us evidence of such phenomena, waiting for us to develop the wisdom and capability to recognize the signs of civilizations that have transcended the ultimate speed limit and open doorways to realms of possibility we can barely imagine. As we reach the end of our journey through the possibilities of faster-than-light travel and alien civilizations that might have transcended the cosmic speed limit, we find ourselves standing at the edge of the known universe, gazing out into infinite possibilities that stretch beyond the boundaries of our current understanding. The questions we have explored tonight touch the very heart of what it means to exist in a cosmos that may be far stranger and more wonderful than we have ever dared to imagine. The speed of light, that fundamental constant that has shaped our understanding of space and time for over a century, may not be the ultimate barrier we once believed it to be. Somewhere among the countless stars that fill the night sky, civilizations may have already discovered the secrets that would allow them to transcend this limit, opening doorways to realms of existence that remain hidden from our current perspective. These advanced beings might be traveling between stars as easily as we travel between cities, communicating across the galaxy in real time, and exploring regions of space that will forever remain invisible to our light-based observations. They could be conducting galactic commerce, sharing knowledge instantaneously across vast distances, and participating in a cosmic community that operates on principles we cannot yet comprehend. The theoretical foundations for such possibilities exist within the mathematics of our most advanced physics theories. Wormholes could provide shortcuts through the fabric of space-time itself. Warp drives might manipulate the very structure of reality to achieve effective, faster-than-light travel. Tachyonic particles could carry information and energy at speeds that make light seem slow by comparison. Extra dimensions might offer hidden pathways through higher dimensional space that bypass the limitations of our familiar three-dimensional world. Yet even as we contemplate these exotic possibilities, we must acknowledge the profound humility that comes with recognizing how little we truly understand about the universe we inhabit. Our current knowledge of physics, vast though it may seem, might represent only the earliest stages of a journey toward understanding that could continue for millions of years. We may be like primitive humans trying to understand the flight of birds, completely unaware of the principles of aerodynamics, jet engines, and space travel that would eventually carry our species to the moon and beyond. The search for evidence of faster-than-light phenomena continues to push the boundaries of our observational capabilities. Gravitational wave detectors listen for ripples in space-time that might carry the signatures of exotic technology. Neutrino observatories monitor the ghostly particles that stream through space, watching for anomalous patterns that could indicate artificial origins. Radio telescopes scan the sky for signals that violate our expectations about natural phenomena. Each new instrument we build, each new technique we develop, brings us closer to the possibility of detecting the presence of advanced civilizations that have transcended the speed of light barrier. We may be on the verge of discoveries that will transform our understanding of what is possible in this universe, revealing that the cosmos is populated by intelligence operating on scales and principles that stretch our imagination to its limits. The implications of such discoveries would extend far beyond the realm of science into every aspect of human existence. Our understanding of reality, our sense of our place in the universe, and our conception of what the future might hold would all be fundamentally transformed. We would be forced to acknowledge that we are not alone, that intelligence in the universe has achieved capabilities that seem almost magical from our current perspective. Yet this recognition would also open up extraordinary possibilities for human civilization. If faster-than-light travel is possible, if other species have achieved it, then perhaps we too could eventually transcend the cosmic speed limit and join the community of galactic intelligence. The journey would be long and challenging, requiring advances in science and technology that might take centuries or millennia to achieve. But the destination would be worth any effort. The development of faster-than-light capabilities would transform humanity from a single-planet species into a galactic civilization. We could explore distant star systems, establish colonies around other suns, and participate in the broader community of cosmic intelligence. The entire galaxy would become our neighborhood, with travel times measured in moments rather than millennia. Communication across interstellar distances would become instantaneous, allowing for real-time conversations with civilizations thousands of light years away. The sharing of knowledge, culture, and ideas across such vast distances would accelerate the development of all participating species, creating a galactic renaissance that enriches every member of the cosmic community. The energy and resources available to a faster-than-light civilization would dwarf anything available to a species confined to a single star system. We could harness the power of multiple stars, mine the resources of countless worlds, and tap into energy sources that we cannot currently imagine. Scarcity might become a concept from the distant past as the entire galaxy becomes accessible to human exploration and development. Yet with such power would come profound responsibilities. The ability to travel faster than light would grant access to other civilizations and their worlds, requiring wisdom and ethical development to match our technological capabilities. We would need to learn to be good citizens of the galaxy, respecting other species and their rights, while contributing to the greater good of cosmic civilization. The possibility that we are already surrounded by faster-than-light phenomena that we cannot detect adds an element of mystery and wonder to our daily existence. Every night, as we look up at the stars, we might be observing the highways of galactic civilization, watching the passage of spacecraft that traverse the cosmos at speeds that make light itself seem stationary. The radio signals from space that we dismiss as natural phenomena might sometimes be the electromagnetic side effects of exotic technology operating beyond our current understanding. The unexplained observations in our astronomical databases might contain hidden evidence of faster-than-light activities that we have not yet learned to interpret correctly. This possibility suggests that the universe is far more active and populated than we currently realize. Rather than a mostly empty cosmos with rare islands of life and intelligence, we might inhabit a galaxy teeming with activity, where advanced civilizations conduct regular commerce and communication, while we remain unaware of their presence due to the limitations of our primitive observation methods. The philosophical implications of faster-than-light alien civilizations challenge our most basic assumptions about the nature of existence. If intelligence can transcend what we consider to be fundamental physical limits, it suggests that consciousness itself might be a more powerful force in the universe than we currently understand. Mind might not be simply an emergent property of complex matter, but a fundamental aspect of reality that can directly influence the structure of space and time. This perspective opens up connections between scientific and spiritual understanding that have been largely ignored by conventional thought. Many ancient traditions have claimed that consciousness can transcend the normal limitations of space and time, suggestions that have been dismissed by materialistic science. If faster-than-light technology involves consciousness-based manipulation of reality, it might validate some of these ancient insights while revealing new connections between mind and cosmos. The ultimate destiny of intelligence in the universe might be far grander than we have ever imagined. If the speed of light is not truly a fundamental limit, if consciousness can manipulate space-time directly, if the cosmos is filled with civilizations that have transcended our current understanding of physics, then the future possibilities for intelligent life become literally infinite. We might eventually develop not just faster than light travel, but the ability to manipulate matter and energy on cosmic scales, to create new universes, to transcend time itself, and to achieve forms of existence that we cannot currently even conceive. The journey from our current primitive state to such cosmic consciousness might take millions or billions of years. But if faster than light travel is possible, then every destination becomes reachable, given sufficient time and determination. As we prepare to rest beneath the stars tonight, we carry with us the knowledge that the universe may be far stranger and more wonderful than we have ever dared to believe. Somewhere among those distant points of light, civilizations may have already achieved the impossible, transcending the speed of light and opening doorways to realms of existence that remain hidden from our current understanding. The cosmos speaks to us through gravitational waves, exotic particles, and phenomena we have not yet learned to interpret. Perhaps some of those messages come not from natural sources, but from minds that have learned to reshape reality itself, beings that have discovered the secrets of faster than light travel, and now explore the infinite possibilities that such knowledge makes available. Rest now beneath the infinite stars, knowing that the story of our universe is far from finished. The greatest adventures in cosmic exploration may still lie ahead, waiting for us to develop the wisdom and capability to join the community of faster-than-light civilizations that may already be traveling the highways of space and time. Sweet dreams await you in the cosmic tapestry above, where light travels at its stately pace while other phenomena race beyond the speed limit, carrying information about civilizations and possibilities that stretch our imagination toward the infinite. The universe holds secrets yet to be discovered, and perhaps the greatest secret of all is that the speed of light represents not an ultimate barrier, but merely the first step on a journey toward understanding the true nature of existence itself.